So good morning, everyone. So I'm Enrico Domanti, and today I will speak about. Okay. So I will speak about my PhD thesis, which is entitled "Quantum Simulation of Z2 Lattice Gauge Theories in One Spatial Dimension." So this PhD thesis was supervised by Professors Luigi Amico and Dario Zappalà. It was carried over here in the University of Catania and in TII Technology Innovation Institute of Abu Dhabi. So today we are concerned about studying gauge theories and lattice gauge theories. So first, gauge theories are theories that are invariant under local space-time gauge transformations. And these theories are at the basis, at the roots of our understanding of fundamental interactions. The first encounter that we have with a gauge theory probably is with the theory of electromagnetism, in which we notice that when expressed in terms of the electromagnetic potential, the electromagnet is invariant under local gauge transformations. And the QCD, or the electroweak interactions, are. And both the theories of QCD and electroweak interactions are gauge theories. The way is the language with which we understand the theories of fundamental interactions. Lattice gauge theories instead are gauge theories discretized on a space-time lattice. These have become relevant in the field of high-energy physics because they are used to approach non-perturbative phenomena such as that of confinement, and this has been epitomized by methods such as the Monte Carlo methods. But lattice gauge theory are also extremely relevant in many areas, many other areas of physics, such as in condensed matter physics, when they emerge as effective description of spin liquids or of topological order, or in relation to the study of ITC superconductivity. So how do we study this theory? So analytically, the non-perturbative nature of some of the phenomena that can be addressed with lattice gauge theories makes it difficult to approach these models. And even numerically, it is challenging, especially when dealing with finite charge densities or real-time phenomena. So one avenue that one can approach in order to study gauge theories has been given by the field of quantum technology. So this stems from an idea of Richard Feynman, who basically said, okay, we want to study models that are inherently quantum mechanical. So we would be better just to use a quantum hardware, this quantum logic, rather than trying to impose this quantum logic on classical systems, so for instance, classical computation. So, and the idea is to use quantum systems as quantum simulators. So quantum simulators are specific systems which are tailored in such a way to reproduce some target dynamics. And they can work in either two modes, either in digital mode, in the case in which they are used as quantum computers, in which we perform some algorithms with the idea, for instance, of reproducing some target dynamics, or they can work in analog mode, which means that we engineer or we tailor the dynamics of this system such that the natural dynamics of this system will reproduce that of the target model. For instance, a lattice gauge theories. And in the recent years, there have been many works in this sense, both on digital and analog quantum computing. So my work is inserted in this context, and in particular, the main protagonist of my thesis is one-dimensional Z2 lattice gauge. And my thesis work is partly on quantum simulation. So we provided some approaches through which we can perform an analog quantum simulation of this model, either on an open chain on a ring-shaped geometry. And then we consider also some theoretical investigation on extension of these models that have some very nice physical. So I will start by introducing the model. So we are studying a one-dimensional Z2 lattice gauge theory in which we have a one-dimensional chain, and matter is represented by anchor bosons or spin degrees of freedom that live in the sides of a one-dimensional lattice, here in blue, while gauge degrees of freedom here are spin-a-half matrices, are Pauli matrices that live on the limits of the lattice. So the Hamiltonian consists of a gauge invariant Hopking term, which is basically the same as in a tight binding model, but assisted by sigma z Pauli matrix, which is the so-called parallel propagator. And then we have an electric field term, which is responsible for the non-trivial dynamics of the system, the analog of an electric field term, as I will explain in a minute. So beware that we are working in a basis of sigma x. So we're working with states plus and minus, which are the eigenstate of sigma x with either plus or minus eigenvalues. And we denote as minus so-called negative electric string, so with an arrow that points to the left, and positive electric string, the plus, pointing to the right. So the local nature of this theory stands in the fact that we have local Z2 transformations that are generated by some operators, GI, that commute with the Hamiltonian at each side of the lattice. This, of course, introduces a gauge redundancy in the problem, and so the Hamiltonian will be block diagonal in any basis of these GI operators. So to fix this redundancy, what we do is that we choose one of the blocks, which means we choose a gauge sector, and the usual choice is to choose all the eigenvalues to 1. This is basically equivalent to considering a constrained Hilbert space, we call the physical Hilbert space, and to establish a Gauss law. But basically, the constrained configuration as such that whenever there is an occupied site, the electric field degrees of freedom needs to flip at adjacent links. This means that the particles will act as sources or drains of the electric field. So this is the analog of a Gauss law or a Z2 theory. And now we can understand better the meaning of the various processes. So in the hopping, basically when a particle jumps from one side to another, the electric field will flip to the opposite direction to adapt to the Gauss law. And we can also understand the meaning of the electric field term better. So let's start from a vacuum state. There is no particles. And in the ground state, the best situation is to have all spin polarized in the negative direction. If we now add two particles on top of the vacuum, by gauge invariance to adapt to the Gauss law, all the strings need to flip to the opposite direction in between the position of the two particles. So we will have an extended electric string between the position of the particles and the energy of this new state on top of the vacuum, which gives the potential that this particle feels, grows linearly with the extension of this string, so with the separation of the particles. This means that we have a confining interaction because we have a linearly increasing attraction between pairs of particles. And as a result, this will form bound states which can address as the analog of the mesons of energy physics in a toy model. So how do we observe this physics in experiments? And so we have proposed an avenue for the quantum simulation of this model on an open chain. So the main ingredients of these protocols are two. In this case, we need a quantum platform that can engineer an XY model, so a spin system with XY interaction. And we want some longitudinal fields at the position of the even spins. And the idea is that we want to encode independently matter and gauge degrees of freedom of the gauge theory of the target model, independent degrees of freedom of the simulator. So we identify as matter degrees of freedom the odd number spin, as gauge degrees of freedom the even number spins. And the idea now is that the longitudinal field at the position of the gauge atoms basically will be the electric field term in the lattice gauge theory, in the target model. The other ingredient that we need is that we want to add a Floquet driving scheme. So we want to add to the time-independent XY model a time-dependent term, which is a driving term, which basically, by Floquet theorem, this means that if we start from an initial state and we look at the dynamics at integer multiples of the driving period, this unitary dynamics is generated by a time-independent Hamiltonian, which is called either the Floquet Hamiltonian or effective Hamiltonian. And the point is that if we work at a very large frequency of the drive, we can proceed in a perturbative expansion of this effective Hamiltonian. And the idea, this is at the basis for this scheme, is that we can recover the lattice gauge theory Hamiltonian at some order in perturbation theory. So this we manage by driving a transverse field at the position of the odd spins. And the idea is that first order terms in first order in perturbation theory are just renormalized XY dynamics. And since they are not gauge invariant in the target model, we can kill them by a fine-tuning of the amplitude of the drive. And at second order, basically with this drive law I'm proposing, we managed to just selectively address with no further effort only the gauge invariant terms of the dynamics. So basically, we demonstrated in the thesis that the effective Hamiltonian up to second order is exactly the Hamiltonian of the lattice gauge theory that we want to simulate. And the point is that now the dynamics, of course, will be some effective parameter, F, which will be perturbatively smaller than the original dynamics, so that it will be a slower dynamics. So we need a platform in which the experimental times allow for an observation of such a slow dynamics. We found it convenient to employ Rydberg atom arrays as a choice of the platform. So we have Rydberg atoms, which are highly excited with large principal quantum numbers in Rydberg states. These have very large dipole moments, so interact very strongly with one another. And the idea is that we encode the two-level system for the spin system in two Rydberg levels of opposite orbital parity. And the reason is that with this platform, the natural dynamics is exactly an XY model. with the difference that this XY model is now long range and is not nearest neighbor. So we have additional steps. And moreover, the range of the interaction goes down like 1 over the distance between the atoms to the cube. Also, this interaction is by nature anisotropic, and basically its strength depends on the angle that the segment that connects two atoms makes with the direction of an external magnetic field. And the advantages of the Rydberg atom platform is that basically by laser driving the atoms, we can obtain all the extra terms that we need for the Floquet driving, meaning both the longitudinal field and the transverse field that we use in the implementation. And also by the fact that they have very strong interaction, the natural dynamics, this J, is very large. So meaning that when we consider the perturbative reduction of the effective hopping in the lattice gauge theory, this will be still fast enough to be observed within experimental times that are typical of Rydberg atom experiments. The only drawback is that we have to deal with long range, because the long range is adding extra terms that might break gauge invariance. But the point is that the tunability of the geometry of the system that employs optical tweezers that can be moved in the experiment allows us to choose a geometry that tunes the anisotropy in such a way that all the leading order terms that are not gauge invariant can be killed automatically by a choice of the geometry. Because there are angles in which basically the interaction vanishes in a certain direction. We choose them in such a way that we kill the non-gauge invariant processes. So basically, what we have demonstrated and the take. Maybe it has to load a second. Just the image is heavy. Okay, so the main take-home message is that we manage to obtain a scheme for the analog quantum simulation of the Z2 lattice gauge theory, in which the dynamics is fast enough. And moreover, we proved here we are showing the percentage error, the percentage violation of the gauge invariance. And we are showing that this grows in time in general, but first of all, by increasing the driving frequency, the error gets lower. And the reason is that we suppress higher orders in the Floquet expansion that might be detrimental for gauge invariance. And also, the long-range interaction after this fine-tuning of the direction is actually not important, at least for typical times of other experiments. That is where this figure is truncated. And basically, we've shown that this white line, the error stays below 10%, which means that for a time scale that is around 2 hopping processes in the gauge invariant dynamics. So we also consider implementation on a ring geometry. And in this case, the implementation is still based on Floquet driving schemes on Rydberg atom platforms. For reasons of time, I will just mention the fact that with this implementation, we are able to introduce an extra degree of freedom system, which is an external synthetic magnetic flux that pierces the ring geometry. And let me focus on the main physical effects that arise from this flux. And so the flux in the Hamiltonian couples to the tunneling of the matter, basically with a phase factor which assists the hopping of the particle. So one thing that we've studied is a dynamical protocol in which we initialize an initial mesonic bound state in a position of the ring, and we let it evolve with the lattice gauge theory Hamiltonian in the presence of this flux. So what we record, this is a kind of a Faraday-Bomb setting in which when the particle evolves, the counterclockwise and clockwise components of the wave function will interfere after circulating the whole ring and after accumulating a phase that depends on this flux. And we record the probability that the center of mass of these particles is found in the opposite position with respect to where it was started. So the interference dynamics that we see is basically strongly dependent on the strength of confinement, which is controlled by this electric field strength H. And basically, the difference is in the fact that it's already qualitative by the fact that with strong confinement, the interference pattern is much neater, let's say, than for weak confinement. And the reason is that when the confinement is strong, particles form bound states which are closely packed together. So particles like to stay in nearest neighboring positions. And as such, the degrees of freedom are only the center of mass moment of the bound state. For weak confinement, we've solved the two-body problem exactly, and what you see is that we have a resurgence of the relative dynamics of the bound state. So basically, these oscillations are due to the presence of extra frequencies that come from the oscillation of the relative coordinates of these two particles. But most remarkably, let's say, if we compare the strong confined case with what you would obtain for a single particle in a tight binding model, what you see is that the interference patterns are basically superimposable. But there is a crucial difference that is, let me show you in this way. If you look at the middle of the figure where there is completely destructive interference, this happens when the counterclockwise and clockwise components of the wave function accumulate a pi phase difference. So they destructively interfere and you record that zero interference factor. So for a single particle, this happens for a value of the flux that is 0.5. For a confined bound state, this happens at half the value of the flux. And the reason is that the two particles that form the bound state are sharing the same flux, and the wave function is basically accumulating double the phase. So what we are showing basically is that the flux-driven interference dynamics is able to record the composite nature of the mesonic bound state as being made of two particles, which is a very nice effect. So I will now present some extension we've built up on the Z2 gauge theory that presented so far. These are more a theoretical investigation. So here we consider basically the extension in which each bond of the lattice now hosts an extra link rather than just one. This means that we will have an extra spin degree of freedom on the extra link. The two links are geometrically taken to close in a loop geometry that will now extend between pairs of nearest neighboring sides. And the Hamiltonian is basically very similar to the one of the previous theory, just accounts for the extra degree of freedom. But there is an additional term which is crucial for our analysis, which is this gauge flux term. So basically, this gauge flux term is the product of the sigma z degree of freedom in the plaquette. So this is basically physically, it's a gauge flux. It's the flux that the gauge field has across the elementary plaquette. It's like a Wilson loop. It's an elementary Wilson loop in the language of gauge theories. And this flux can either be Z2 value. It can be either 1 or -1, depending on this. It can be either 0 or pi, depending on this product, be either 1 or -1. So we again have some sort of Aharonov-Bohm setting in the sense that when a particle hops, it effectively has two paths to go through. And if the flux is 0, then we have constructive Aharonov-Bohm interference. The particle can hop to the next side. But if the flux is pi with destructive Aharonov-Bohm interference, the particle cannot hop. So if you localize now a pi flux in a chain, what happens is that the chain is effectively broken because all particles that are located in the left part cannot hop to the right side. So this Aharonov-Bohm interference in this case is what causes one phenomenon of this model that we've named dynamical Aharonov-Bohm caging. So basically, we found that in the ground state of this system, depending on the gauge flux term and on the filling fraction, on the density of the particles, you can get a situation in which the chain breaks into partitions. Now, these partitions are isolated from one another because of these pi fluxes not allowing the particles to hop from one to the others. So particles are caged inside these partitions. And they are usually caged in pairs, 2 particles per each cage. And this cage can be of different sizes, depending on the parameters of the model. And they can be, for instance, dimers, so cages of 2 sides with 2 particles trapped inside, or cages of 3 sides where 2 particles are trapped inside. So we call it dynamical Aharonov-Bohm caging because in a way it is similar to a phenomenon that was introduced by Dussault-Vidal in studying 2-dimensional structures or one-dimensional or quasi-one-dimensional structures in which an external synthetic magnetic flux causes a similar effect, which is a localization of particles without disorder due to the Aharonov-Bohm destructive interference. So to study the effects that this dynamical Aharonov-Bohm caging has on this model, we fix for now a filling fraction, a specific filling fraction. So the number of particles over the number of sides, say, is 2/3. And as a figure of merit, we take the charge gap. So the charge gap is an estimation of the energy cost to create or to remove 2 particles from the system in this case. And as you see here, it's the charge gap reported against the electric field strength on the y-axis and the flux, amplitude on the x-axis. And there is a parameter space in which this charge gap is open. And this is a signature of an insulating phase. It's a Mott insulator. And in this Mott insulating phase, what we see is that dynamical Aharonov-Bohm cages produces cages of 3 sides. It's what we have called trimers. And the point is that since 2 particles are contained in the trimers, and the filling is fixed to 2/3, basically these trimers are commensurable with the size of the chain, meaning that they completely cover the lattice. So in a way, they are stuck. They cannot move. And this comes with a spontaneous symmetry breaking of the lattice translational invariant. And lattice translational invariance here is reduced to 3 size translation. So we have a sort of crystalline structure. And outside of the of the not insulating region, the charge gap is closed. The system becomes also gapless in the sense of spectral gap. And we have the description of the phase is a Latinger liquid. So it's a gapless phase of matter. And in this case, for very small electric field, we have two possible situations. At the left of the not insulating region, we found that the chain remains fully connected. So the quantum fluctuation of the flux that are introduced by the electric field reconnect the trimers together. So the chain does not form cages anymore. On the right of the not insulating region instead, quantum fluctuation of the flux induced by the electric field tend to squeeze the size of the cage to two-sides cage, to so-called dimers. Now these dimers are smaller, so they are free to move inside the chain. And the crucial part of this work is that we found out that the dimerized regime extends to very large electric fields. And this for us is important because it's a crucial difference with the Z2 theory, because in the Z2 theory, the standard, dimers can form a strong electric field, but cannot form a small electric field. And the reason is the following. At very large electric field, dimers form because of the strong confining interaction between the particles. So particles like to stay in nearest neighboring positions. While for very small electric field here, the formation of dimer is driven by a completely different mechanism, which is that of Aharonov-Bohm interference. So basically, we proved in the thesis that these two regimes are perfectly equivalent in the sense that they are described by the same perturbative model. We have derived it through Schiffer-Wolf approaches. And basically, this means that dynamical Aharonov-Bohm caging in this setting is responsible for a new mechanism of strong confinement, even in the absence of strong electric field strength connecting to particles. So let me also note that this two-thirds filling is not particularly special in the sense that the same physics can be found for other filling fractions. If we've done a more complete study in the presence of a chemical potential in which we find other not insulating regions with cages of different sizes. So with this, I would like to turn to conclusions. So we have demonstrated that basically that it is possible to perform quantum simulation of the Z2 lattice gauge theory with a current experimental platform based on Rydberg atom arrays. And we've also provided implementation in periodic boundary conditions in which basically Aharonov-Bohm oscillation tells us something about the internal structure of the confined bound states. Moreover, we have considered an extension of this Z2 model to adding two links to a Z2 loop chain. This comes about with the new phenomenon of dynamical Aharonov-Bohm caging that is responsible for a new mechanism of strong confinement. So what we are planning to do now is to provide an implementation for the loop chain with a similar idea to that we applied to the standard Z2 chain, and to consider extension to account for multiple loops because we believe that they have quite interesting features. With this, I thank you for your attention.